You're running low on chairs. That one looks like it's hosting a backpack. Maybe it can be repurposed as purses on a person who's holding that.
Yeah, we can, Dan. We can grab chairs from outside too if we need a couple more.
That's the guy at the reception where you should get a chair from.
Yeah. Okay, I'd like to welcome everyone.
Yeah, just right at theater, yeah.
Okay, not sure what that was about, but I'd like to welcome everyone to the March Northwest C++ Users Group meeting. Couple of one major announcement. Next month, we will still be meeting here just a half hour early. So they're continuing to kind of align the different user groups going on. So next month we will start at 6:30 and we will finish at 8. And I'll make a big flyer. So see, Chris isn't here tonight. He also did not leave me any information on conferences and stuff, so no information on that from my side. Does anybody else have any other announcements before we dive in? Okay. Oh, one more I was going to mention. Toward the end of the year, we will be doing a, it's going to be like, I think it's September, lightning talks. So if anybody has a small talk they want to give, 5-10 minutes type of thing, we're going to do a whole session just for those. So we'll just collect them all up. So with that, I'm going to turn it over to Dan and speaking about linear algebra and C++ and the Eigen library.
Okay.
I will give you the camera.
Uh-oh.
There he is.
You don't break it. Hey, well, oh, there he is. Hey.
All right, yeah, behave yourself. You're on camera.
Okay, well, welcome everybody. So yes, that's the topic of talk tonight, linear algebra and C++, a little bit about the Eigen library, and then talk a little bit about what's coming ahead in C++ 26. Okay, so kind of an outline of where we'll go with this. First, start with a little history and the C++ 98 state of the world, actually as it was in around 1998. Then we'll talk about open source linear algebra libraries that came in over the years. That includes Eigen. Then we'll look at mdspan, which is now in C++ 23. And the reason for that is it is instrumental in the C++ 26 stud BLAS proposal that has been accepted. And then we'll dig in more closely with the Eigen library, and then we'll conclude with again going back to stud BLAS, and then look at how you could use them together. Okay, so let's take a little trip back with Father Tiresias to 1998. And as long as we're flying back to 1998, we'll go in style as it was at the time in the venerable 747-400, beautiful aircraft. Also, by 1998, actually, it was late 1997, I believe, that the HAL 9000 computer was operational at the University of Illinois research facilities in Champaign-Urbana. On your CRT monitor, big old things, remember those? Get a hernia, carry, and you might have seen something like this. So old Amazon.com or Windows 95 fun days. And, we were just having that discussion earlier. I wish I'd hung on to my Amazon stock from 1998, but that's another story. But speaking of investing in stocks, this was also, we're building up to the dot-com bubble. And at that time, it was okay to invest in a company with negative price earnings ratios as long as it had a .com at the end, like the globe.com or pets.com. Okay, so where were we, say, in 1998? Speaking from personal experience, I was in financial programming, on financial programming, but I'd come from,
Hang on.
okay, all right.
Yep, you're good.
Cool. But the mathematical programming I had done, what I was used to was Fortran. And Fortran, back in college and grad school, had some really nice support for linear algebra. So we had multidimensional arrays. We had BLAS, basic linear algebra subroutines.
Actually, it's sub-pro.
Is it? Oh, okay.
Small, it's a little bit of trivia.
Okay, I might have that
So
elsewhere.
I think a lot of people say subroutines.
Or I might have, yeah.
So,
Okay, sorry about that. Yeah. LAPACK, linear algebra package, and also IMSL, which was a commercial library, but typically available on university Fortran platform. So, life was pretty good. But around this time, so in finance, C++ was being touted as the next great thing. I mean, everybody wanted C++. It was, everybody was jumping on that boat. But for those of us with scientific programming experience with Fortran, we found ourselves in a bit of a quandary because all this stuff vanished. And so we're left with, well, now what? Well, there were a few contrived solutions, such as using a vector of vectors, not exactly palatable, nor was a two-dimensional dynamic C array. There was and still is, but with C++ 98, and before you start throwing tomatoes at me, was val array. And personally, I thought it was a great idea. It was exactly what I needed at the time to build a decent matrix class. Why? Well, you could represent a matrix with a two-dimensional val array. It offered built-in element-by-element mathematical operations, and also element-by-element CMath-like functions like trigonometric functions and natural log, so forth. There's also an apply function that works a lot like stood transform. So with this, you could compute row by column dot products in two different matrices, and thus it made it very easy to implement matrix multiplication. Unfortunately, and as many of you know, there was some controversy and some downsides with this, namely inconsistent implementations. At the time, expression templates had just been discovered, and so again, I wasn't in on this, but as I understand from the history, there was a debate whether or not to require expression templates in the implementation of val array, and it turned out this was not required, and so there was a wide variance in performance.
Excuse me, can I ask what an expression template is? I just don't remember.
Oh boy, it's where you can. An example is, suppose you have some kind of a vector class, and you want to be able to add vectors. You can arrange it so that for an arbitrary number of vectors, you can add them, and you align the addition in a lazy way so that you don't create temporary vectors along the way. You just wait until all the data is in, and then it's the addition is not computed until you tell it to. So everything it's like you put everything in, but it doesn't do anything. It's just holding the data there And until you say go, it doesn't do anything. I don't know if that's a reasonable explanation, but it's one way it's applied.
May I?
Yeah, please. Yeah, this is the expert here. So
Well, yeah, you actually make my student invented them.
what's that?
So my student invented them.
Well, I know. Yeah, that's true. Yeah.
Todd Belfies. No, so the basic idea is that at compile time to use templates to create basically a parse tree in the text system or in the template system. And then the assignment evaluates the compile time parse tree, which lets you do things like, collapse repeated addition of vectors into a single collapse loop.
Yeah. And that's true. Yeah, it's not until you call that assignment, it doesn't do anything. So the other thing was, in order to access an individual row or column, you could get this via what's called a slice array, but this was only a view of the row or column and does not support, because they're still around, most of the val array functionality. So if you wanted to do things like add and subtract or apply one of these functions and so forth, you'd have to actually use it in the construction of a new val array object. So you took a performance hit that way. So again, speaking from experience, it did what I needed it to do at the time. And we did use it for a while. For what we used it for, the performance was reasonable, but there were downsides with it. And again, it's just my own opinion. It's very unfortunate because it's really a great idea, but again, tomatoes throwing at me, cabbages. One other option that you had was to try to convince your boss to invest in a decent commercial linear algebra library. Sometimes you win, sometimes you lose, but on occasion we had this luxury and life was good. Okay. How did this happen? Okay, so actually, and so Andrew would know a lot more about this, but there were open source linear algebra libraries that started to hit the scene. Actually, this was first released in 1998 and supported, well, still does, I guess, but well, we don't know what the status is really now. But sparse and dense matrix formats, basic linear algebra arithmetic on vectors and matrices, inner products and norms, this sort of thing. Then a few years later, Boost BLAS came along, where it's similar functionality as MTL, in other words, BLAS. And I was going to say, but even according to, I mean, this is actually off of the Boost website, the documentation there, it offered good but not outstanding performance. And its last improvement was in 2008. And this is actually in the facts on the website. As they also say in the documentation, there came along what they called next generation linear algebra libraries, and this list is not exhaustive, but Eigen, which came around in late 2006, Armadillo in 2009, and BLAS in 2012. The first two are very popular in finance, and that's my area. So the examples I'll show later actually come out of finance. I've used both of them. I'm a lot more familiar with Eigen, so you use that a lot more often. But again, they're both quite popular in financial applications. BLAS came a little bit later. I've not tried that. There is a really decent talk though about it from from CPPCon 2016, back when it was here in Bellevue. Wasn't that great?
Mm-hmm.
Yeah.
I think that's where we met, actually, in 2016.
Yeah, I think that's right. Yeah, the open content session. The main developer, Klaus Egelberger, was the speaker for this. So if you're interested, there's a really good talk. Okay, then moving forward into the present day, we now have mdspan in C++ 23. What is this? It is a polymorphic and mutating multidimensional array reference or view of a container whose elements reside in contiguous memory. So for example, stood vector, or later on, as we will see, a vector XD type in Eigen. One more type that you could use is an MD array, which is the owning analog of mdspan and is, I believe, scheduled also for C++ 26. Why is mdspan important? It ties in with stood BLAS proposal 1673, which has been approved for C++ 26. This is, as they call it, a free function linear algebra interface based on the basic linear algebra. So what was it again? Subprogram. And so what this means is you can use any BLAS library that you want, but your code will remain standard, which is a really good thing for cross-platform computing. But why mdspan is important is this is how matrices are represented in stood BLAS. And although the choice of the BLAS library is arbitrary, there will be a default version included with most of the major compilers and vendors. So it's also available. There's a reference version that's available out on GitHub, and I'll give you the information on that later at the end of the presentation. Okay, so that's kind of an overview from past to present. Now let's look at the Eigen library. Okay, so what is Eigen? It is a C++ template library for linear algebra. So matrices, vectors, numerical solvers, and related algorithms. And the first version came out in December of 2006. It's now at version 3.4 and is licensed under the Mozilla public license. It was originally released under GPL, which made it a lot more restrictive. It moved to the LGPL, which is a bit better, but as of version 3.1.1, it's now licensed under the more liberal Mozilla license. Also, one nice thing about Eigen is the documentation is quite good. It's popular within a number of domains, in particular, again, finance, also medical and pharmaceutical research, in particular, pharmaceutical simulations, data science, and experimental physics. And more specifically here, it's included in the TensorFlow library, so that data science, machine learning connection. The STAN math library, which is used, again, a lot in medical and pharmaceutical research. And it was also adopted for the Atlas experiment tracking software, which is used at CERN with their experiments on the Large Hadron Collider. So Eigen offers dense and sparse matrix representations. For this talk, we will be mainly concerned with dense matrices and operations. The core class for dense operations is the Eigen matrix class. It's part of a class template hierarchy, which looks something like this. Most of the member functions and operators are defined, though, on the matrix base class. So Eigen uses expression templates and lazy evaluation, so its performance is quite good. I have not run performance tests myself, but some of the references that I've read and talks I've attended, it's always compared very well with its competitors. Another nice thing being a template-only library, so it's header only, and so it makes it very, very easy to include in a C++ project. You can use other BLAS libraries if you want, but out of the box, if you're using it in a project, you just specify where it's located, and that's it, and away you go. There's also a vector class in Eigen, and this is a special class of the matrix. So it's an m×1 column vector. The matrix class supports the usual numerical types, so int, float, double, and std complex double. There are various aliases of the matrix class. So there are, first of all, fixed square matrices up to 4×4. So a matrix 4I is a 4×4 matrix of int types, and matrix 3F, a 3×3 matrix of float types. But for most applications, you're not going to know the dimensions a priori, and so we need a dynamic type of matrix. And here there are also aliases available. So matrix XD is a dynamic m×n matrix of double types, and similar for matrix XD. And then there's also matrix XCD, which is a matrix of complex double types. These aliases are very nice to have, because if you had to, I think there are about 6 template parameters, and it gets a bit messy, so it's a lot easier just to say matrix XD for a matrix of real numbers. The two that we're going to be concerned with here are going to be these matrix XD and vector XD. So some matrix XD examples. You need to include the dense header file, which is in the Eigen subdirectory. And we're going to be using matrix XD a lot, so we'll just put in a using statement. Lighten the notation a bit. So one way you can create a matrix is just enter the data row by row, each row in a pair of braces. However, one thing to note, and this can be a bit confusing, is that even though you enter the data in row major order, it's stored in column major order. I don't know why they did that, but it is what it is.
Fortran.
Right, but why you would enter it in row major order, but store it in column major order?
Oh, well, the notation is what you'd expect.
Okay.
Yeah, but then column. I mean, it is, you're right.
Okay, yeah, I see your point. Yeah. And it is easier to think of putting the data in this way. So another thing you can do is just tell it the dimensions that you want in the constructor, and then add the data in later. One way you can do this is with the stream operator, as you see here. So this would be a 4×3 matrix. And also you can do the same thing, but then just assign each value element by element. For vector XD, it's very similar. So you can create, again, this is an m by 1 column vector. So you just put the data again in braces, but note that how this is different from a standard vector. So you need the braces inside to hold the data and then the braces outside for construction. Alternatively, again, you can tell it the number of dimensions that you want and then add the data later with the stream operator, or you can again assign it element by element. Also, the stream operator is overloaded for see out, so you can just see out the contents of a matrix or a vector to the screen. Again, in reality, you're not going to hard code your data, but this shows you how you actually construct these objects and add data to them, but you'd be getting your data from an interface or something. Okay.
Question, what does it mean to have dense versus sparse matrix?
Dense means that, like what you see, you've got something in every element. Sparse means you've got a lot of zeros essentially, and because of that, then the implementation of things like multiplication or certain decompositions and so forth is different because there are more efficient ways to do it.
Are they actual zeros or are they just?
Yeah, the zeros.
Actual zeros.
Yeah.
Well, actually,
They're not
not stored, not just blank memory or non-represented memory.
Okay, yeah, all right.
They're not-
Yeah, I'm sorry, I'm thinking mathematically. Never mind.
Okay.
So, I'm sorry.
So does it mean that there's no, is it like not a number or is it actual zero?
In a sparse matrix, they just don't store.
Yeah, it's not
this
stored,
zero,
just-
just store.
Yeah, think of memory, it's fragmented essentially in memory rather than contiguous. Well, it's probably not the
They
right.
store all the data contiguously. What you have to represent the matrix.
Yeah,
You have to store the row number, the column number, and the
Right.
value. Typically those will in high performance
yeah, it's built in.
implementation, those will
Right.
be all contiguous. Yeah.
Right, but you don't have memory allocated for the spot where you don't have data. That's what I was trying to say. But said that badly.
But in the application though, it's just the case you don't have data for that position. You might just have, the data itself might be sparse. And then what goes on behind the scenes on the computer side is the experts have said. Glad you guys are here. Okay, so a very common problem in finance is you might be given a correlation matrix, say, of returns from assets in a portfolio. And it's just, as a simple example, suppose we have a small portfolio of 3 assets. And so those are the correlations of the returns for each asset. And you would be given a vector of the individual volatilities, or in other words, the standard deviations of the movements of of each individual return, independent of the movements in the other returns. But in most financial applications, what you really need is the covariance matrix, sigma. And so what you need to do is you need to compute that. And so the first step is going to be forming the diagonal matrices on the left and right hand side from the data in this vector. There's a member function in Eigen called as diagonal, which will return a lighter weight view of diagonal matrix of diagonal matrix containing these vector elements, which is pretty handy thing. So that makes computing the product very easy. So you just call as diagonal on the volatility vector on each side, and you carry out the multiplication. In Eigen, the star operator is defined as matrix multiplication, not element by element multiplication. So it all flows very nicely mathematically. You're not calling member functions for multiplication. It just as you write it out in mathematics, you program it in Eigen. And then we can return the result as a matrix object. And so that's how it lines up mathematically. Again, the operator here is defined because we're just multiplying 3 by 3 square matrices. And so the matrix multiplication is defined. And so is operator star. And so the result is a 3 by 3 covariance matrix. You can also do vector by vector multiplication, but you do have to be a little careful here because remember, star is defined as matrix multiplication. So, and remember, U and V are technically column vectors. So if you want to carry out this multiplication, you have to transpose one or the other. If you transpose the first vector, that's just going to give you the dot product. But if you do it the other way, it's going to return a singular 3 by 3 matrix. So you need to be a little bit careful here. However, I believe this was probably the motivation they had in mind was to define a dot member function. And this way, it doesn't matter. It's commutative and safer. Okay, and then matrix and vector addition and subtraction, again, it just flows like it would a mathematical statement. So if you have two matrices A and C and you want to add them, it's just A plus C and you're done. And then you can see out the result. And similar for two vectors, say U and V again. In this case, we'll subtract them. So just U minus V, and I didn't see out it here, but you get the result. Now, one really, really cool thing about Eigen is it is STL compatible. This is really a great feature. So you can iterate through an eigenvector and apply STL algorithms. So as an example, we might say populate a vector XD with random numbers drawn from a T distribution using random in the standard library and apply the generate algorithm. And then suppose we want to find the maximum element in that result, we can apply the max element algorithm. So we create a vector XD with 12 elements, and then we'll set up Mersenne twistor random engine with a seed of 100 and T distribution with 5 degrees of freedom. And then as you can see there, it's just a case of applying the generate algorithm as you would with any standard container. So again, this is a pretty cool thing.
Do the vectors also satisfy ranges? Okay.
No. And then to find the max element, again, it's exactly the same thing you would do with a standard container. Okay. Eigenvector types can also be used with STL containers in standard algorithms. And this is also very cool. So first example, suppose you have a vector XD and a stood vector, and you want to compute the dot product of those two vectors. So what we'll do is create a stood vector with the same size as U, and then we'll apply the same generate algorithm and generate 12 more random variates from a T distribution. And then to compute the inner product, again, it's exactly the same as if both U and V were vectors. Another example is suppose you want to take the vector sum of these two vectors. We can use stood transform, and furthermore, we can use the ranges form of stood transform. So create a new vector XD to hold the result, and then transform UV with the plus operation. And then each element gets stored in the result W, and you're done. So again, this is a very, very nice feature of Eigen. Eigen also has unary expressions that are similar to stood transform. So, and suppose we have a matrix XD, and suppose we want to square each element. So again, it's just like an auxiliary function in a standard algorithm. You could also apply a function object or an external lambda, again, just like stood transform. Okay. Eigen also offers a wide variety of matrix decompositions. And so again, my background is in finance, so examples I'm going to use. However, I think they're general enough that you should be able to follow along, no problem. So again, this list is by no means exhaustive. There are actually quite a few available, but in particular, there are QR and singular value decompositions, which can be used for multiple regression problems. And in finance, a particular case of this would be fund tracking, which I'll show momentarily. Also, okay, here's a trivia question. How do you pronounce that name? This has been a debate of, decades.
Olski.
Olski.
Okay, Koleski, that's
Tyler.
anyone else? Some people would pronounce it Choleski. I had a Russian student.
Do that, but
And I asked him, he said, yeah, it would be Choleski
In Russian.
in Russian. However, Choleski was French. CHO is pronounced show. So it's in preparation for this, I wanted to, I taught it all these years. I said Koleski, and then I had the Russian student, and so I started saying Choleski. It's like, I'm going to settle this once and for all. It's like, no. It's wrong on both counts.
I've used it for years and it was Cholesky to me, but who knows?
Yeah, right. Yeah. So anyway, we'll stick with Choleski unless I revert to my past. So a common problem in finance is you need to find the Choleski decomposition of a covariance matrix in order to compute correlated random normal numbers or random normal variates. And this is the case in where you're using Monte Carlo simulation, where you have an underlying stochastic process where you need correlated normal variates in your model. And a couple of examples are basket options of valuation. That's where you have an option, say, on more than one underlying asset. And as you get into, like 6 or 12 of them, you're pretty much going to be using Monte Carlo simulation. Also, portfolio risk management, again, the same. You've got a lot of different assets and that they'll map to different asset categories, but that matrix could be easily 1,000 by 1,000. So what you need to do for in these cases is you need to compute the Cholesky decomposition and then multiply it by a vector of independently and identically distributed normal random variates. And then your result is a vector of correlated normal random variates. There's also principal components decomposition, and this is where you're, in a sense, removing the correlations and distilling it down to what are the main drivers of whatever it is that's happening. So, for example, yield curve dynamics. What are the main effects driving changes in the yield curve? Or also measuring feature importance in a trading strategy. So what are the factors involved that will give you a good trading signal, for example? So we will look at an example of using the QR decomposition for a fund tracking problem. And then later on, we'll return to the Cholesky decomposition, but after we've looked at stood laws. So linked together, as you'll see. Oh, and for the record, historically, it was André Louis Cholesky, but from 1875 to 1918, mathematician, geodesist, and surveyor, and French military officer, was killed toward the end of World War I, unfortunately. Okay, so looking at a regression problem, this is a common problem, say, for a pension fund manager, where the manager will take, say, a small portion of the assets under management and entrust it to a hedge fund firm who will invest it, say, in a fund of hedge funds. So there's there's some form of a contract, or the fund of funds says, we will have these ranges of allocations in these different hedge funds in this fund of funds. But they're very secretive about it. They don't have to disclose their information like mutual funds. So it's a bit of a black box. And so the manager might want to know, well, is the hedge fund manager sticking to the promise? And one way to do this is to distill the target fund returns into underlying, or the what are called hedge fund style indices. And this data is known. So this is publicly available. So for simplicity, we'll just assume it's a fund of 3 funds. And we'll assume there are n days of data or observations. And what we want here are the best fit estimates, the least squares estimates, beta 1 hat, beta 2 hat, beta 3 hat, that gives us a fit for the linear regression equation. In problems such as these, we typically drop the intercept term, so don't have to worry about it here. We will assume that the number of observations n is much greater than p, number of funds, which is 3. And so, therefore, we can use the householder QR decomposition, which is fast, but if you have a system where n is starting to get close to p, or an unstable system, then this decomposition will break down. So you might want to look at something else like singular value decomposition, and there are other options, which, however, tend to be slower. But for cases such as these, we're perfectly fine. So as an example, suppose we have data over 30 days with the vector y containing the daily target return. So this would be the returns from the fund of hedge funds. And a matrix X, so with our predictor data, containing the fund style index returns in each column. Setting this up in Eigen, again, we'll just hard code it here, but you wouldn't do this in the real world. And we'll just put it in by row first, and then we can use another member function transpose in place, which will transpose the matrix X for us. And the vector Y, and we instantiate it with the data. Excuse me. And then it's very, very easy. Excuse me. Okay. For Korean food earlier, it's kind of hit me. Love that stuff. Computing the beta coefficients then is really, really easy. All you need to do is call the member function householder QR on the matrix object. That returns a householder QR object, which has the member function solve, and you just put the response data in as its argument, and you're done. And it returns a vector containing beta 1 hat, beta 2 hat, beta 3 hat. And you're done. Very, very easy. Okay, so now we're going to fly back to the future, and instead of 747, we'll be riding on a new 777-9X. And on your nice big flat screen monitors, you might see something cool like Compiler Explorer, Chat GPT. Okay, so what is STUD-BLAS? This is, again, proposal 1673, and from the proposal as stated, it is a C++ standard library dense linear algebra interface based on the dense basic linear algebra sub. I forgot what you. Anyway, BLAS. Blah, 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 yada, yada, yada. In the code, it will fall under the namespace stud linalg. And just some examples here. In the left-hand column, this is how you would write them in Fortran. The leading D stands for double. That could also be F for float, C for complex, or Z for complex with double real and imaginary parts. The middle column is how these same functions will be represented in P1673. And on the right, these are the general descriptions. There are, so for example, matrix product at the end, that's the general form. There are also specific, there's a specific overload for just multiplying A times B. And we'll see some examples coming up. Okay, so again, back to some common problems in quant finance. And again, these involve the covariance matrix. But this time, well, let me see. We're also given a vector omega of portfolio weights. So this means the percentage of your assets that go into each asset. And so the sum of the elements in this vector need to sum to 1. unless you're leveraging, but we won't go there. It is possible to have a negative weight, which means you shorted that asset. I'm more than halfway into this, but I'm just not sure if I face this way, so I face the camera. But you can hear me okay?
Yeah.
Okay. So one task is to calculate the portfolio variance, which you get by computing this quadratic form. And as mentioned before, another common task is to calculate the Cholesky decomposition of sigma. So for the portfolio variance, we can just use STUD-BLAS if we want, because it supports matrix and vector multiplication. But you can't compute the Cholesky decomposition with it. So for that, we'll move to Eigen. But what I hope to show here is how you can use them together and exchange the data between the two. And this is a bit hot off the press. So I've not really worked with STUD-BLAS that much. In fact, this was the first time I actually played around with it. So hopefully this will all go well. Okay, so to compute the portfolio variance, first of all, we'll just in the reference code that's available for now, they've put it under STUD experimental Lin-Alg. So we'll use the alias that you see here. They also use that in the reference code. Now, the way mdspan works is it's a view of data that's stored in contiguous memory. It doesn't really matter what it is as long as it's in contiguous storage. And also, again, we're not going to hard code our data in our program, but just to show how this works, we'll just assume the data comes to us in a vector. So there's the covariance matrix data. And the weights are stored in another vector. Note here that I'm using CTAD, so class template argument deduction. Just again, a nice thing, it makes your code a bit cleaner. Also, though, this is a quadratic form, so in STUD-BLAS, the way we need to do that is compute the left-hand product. So the transpose of the vector times the matrix, that result will be a vector. So we'll need another vector in which to store that result. I'm sorry, that actually comes next. We'll assign to n the size of the vector. We use long because we need long types later in Eigen. Okay, now this is what I wanted to say is that we need intermediate storage of that omega transpose sigma product, which is a vector, so we'll store it in this vector here. But as far as Lin-Alg is, or STUD-BLAS is concerned, you're just you're creating this vector. You'll have an mdspan that refers to it, and then when you get the result, then it will be placed in that vector, but it's represented by the mdspan in STUD-BLAS. If that makes sense. So to set up the mdspan objects, see, so the way this works is you create mdspan, and then the first argument is the memory address of the data. And then the second argument, you have to tell it how many extents there are and their sizes. So, and using CTAD, you can do this implicitly. Just you have n, so that says, okay, there will be 2 extents, each with size n. And then similar for the two vectors that you see in the next two lines, but those are one-dimensional, so you just have one in each. Okay, so now let's compute the quadratic form using BLAS. Okay, the left-hand multiplication, we call the function matrix vector product. Now, this expects the matrix to come first, and in this case, it doesn't care about the transposes and so forth. It just, and again, this is all new to me, so I don't know exactly what's going on behind the scenes, but in using it, it doesn't matter which order you put them in, you'll get the same result. And then the result will be stored in the third argument you see there, MD inner matrix vec, which is actually an mdspan, but again, behind the scenes, it's referring to a vector. And then the next step is to compute the dot product of the remaining two vectors. And so here we use the dot function in BLAS. And the result you get is about 2%. Okay, next task, Cholesky decomposition. So again, we have our covariance matrix. It's symmetric and almost surely positive definite. So that means by theorem, there's a lower triangular matrix L such that sigma can be decomposed into the product L times L transpose. That is the Cholesky decomposition. So to set this up, what we'll do is we'll grab the data from the mdspan MD Cove matrix. And again, you just put in the memory address. What we're doing here, though, is we're using an Eigen map. This is also a view, but it can be used like a matrix XD. I'm not able to find an explicit answer for, what exactly it is in the documentation. But again, by using it, it's getting a bit hand wavy here, but it's like a pseudo matrix XD. So it's a view. You don't actually have to create a whole, a separate matrix XD object. So it's more efficient. But you can use it in eigenfunctions as if it were a matrix XD. And then it's very similar to the QR decomposition, although I'll do it in two lines here. We create an LLT object, which is the Cholesky decomposition in Eigen for L times L transpose. And in the argument, we just take in the Cove matrix map. Once we have that, then again, it's just a case of calling member function on the LLT object matrix L, which gives us the L matrix. And we return it back to a matrix XD object. Now, these results could then be mapped back to a separate mdspan. And so matrix XD also, you can access the memory address with the data member function. And again, we have two extents, each of size n. But oops, if you print that out, it's upper triangular. Again, that's because Eigen stores data in column major order. So what we actually need to do is create a column major mdspan. And in mdspan, you have a choice of layout. The default is layout right, which is row major. But you can create a column major mdspan by using layout left, as you see here. So you create a mapping, layout left mapping called col major. And again, two extents, each of size n. And then when we create the mdspan, we again give it the memory address of where the data is. But now for the second argument, we use the layout parameter. And by doing this, now if you iterate through and print it out, you get a lower triangular matrix. Okay, so that's, that's the presentation, but just to summarize, we looked at linear algebra options going back to C++ 98 when it was rather limited. Along the way, though, we started to see more robust open source libraries in the mid to late 2000s, namely Eigen, Armadillo, BLAS. There are others. These are just the ones I'm familiar with. And again, I've worked with Eigen and Armadillo. I also used BLAS many moons ago. It did what we needed it to do. But then as Eigen came out, this turned out to be more useful for, at least for finance. We looked at Eigen. So again, this is a header-only library based on expression templates, and being header-only again makes it very, very easy to include in a C++ project. It's popular in quant finance, pharmaceutical applications, statistics, applied physics, data science, among others. It gives you basic linear algebra functions and operations, linear solvers, matrix decomposition, and also the transform-like function that we saw earlier. And then the BLAS interface proposal, which has been accepted into C++ 26, so coming soon, offers matrix and vector addition, subtraction, multiplication, so forth. Norms, some other things. But if you need decompositions, then you can capture the data in an mdspan by using an Eigen map, apply the decompositions and so forth. You can map the results back to an mdspan if you like. So some references. First of all, the Eigen documentation, which again is really, really good. There's a lot of examples, which is nice. Just it makes such a difference. Just give me an example how to do it. Okay, that's how I do it. Okay, now I can get on with the job. So it's such a simple concept. Why doesn't be here all night? If you want to learn more about Eigen in quant finance, QuantStart is a really good website for quant finance information news. And so they have an article about using Eigen for quant finance applications. Also, there's a PDF available that tells about why and how Eigen was chosen for the software that's being used at CERN. There's also the STUD-BLAS proposal itself, which you can read through if you like. But, and also the reference implementation is available on the Cocos GitHub site. And rather than reading the proposal, though, if you want to learn more about STUD linear algebra, I highly recommend Mark Holman's talk last year at CPPCon. It's available now on YouTube, and if you want the slides, CPPCon GitHub site. But it was a really good presentation. And also a bit of a shameless plug, but a lot of this came from chapter 7 of a book that I'm writing and should be out later this year.
We decided that.
Yeah, I got my animal.
Is that a cat or is it something else?
It's a cat.
Ah, very cool.
Yeah, kind of looks like
a fat cat.
Yeah, which it kind of resembles our cat at home, a fat and obnoxious cat. But to quote Ian Anderson when he was promoting a Jethro Tull album some years ago during a concert, he says, "I'm not asking you to buy it. If you can't afford it, just borrow it from some rich bastard." Okay, so if if you get into this and you have any questions or anything, feel free to contact me. I'm the student program coordinator for CPPCon, so I have a CPPCon email address. Also, if we're not connected on LinkedIn, feel free to send me an invitation. And so with that, thank you very much. And do you have any questions? Comments? Insults, flames, objections?
Is it possible in Eigen to choose between row major and column major storage?
Not that let's see, yes, there is a way. Can't do it.
You mentioned that Eigen was used for TensorFlow. Do you know if it's also used for PyTorch?
Not that, I don't think so. Just, yeah, I had a look, but I didn't see it.
I've got just a math question, not necessarily related.
Ask him.
Okay. I may get this wrong, so I'm not a math guy. You give me a definition, simple definition of what an eigenvector actually is. I mean, I've gone through it, I've seen the math, I can look it up, I can do stuff. What is it?
Okay, well, right, so no, that's a great question.
You could
So-
write it on the board.
Well, no, well, the intuition of it is, so you have some linear system, so.
Yep.
You have a matrix. Eigenvector is, what's called a characteristic vector or something like that. You multiply it. The matrix acts like a scalar on the eigenvector. And so when you multiply the matrix times eigenvector, it acts like a scalar. So it'll scale it by some value, the eigenvalue.
Say that again.
It's like some combination of inputs where it's like along this particular direction,
It's
whatever.
it's
It's
the,
got a vector pointing off in space and it's described by the
Right,
matrix.
but
And you're scaling it?
But when your system acts like a one-dimensional system in this direction.
Yeah.
Like you-
Got it. Okay.
So it's just, so yes, matrix A times, if it's an eigenvector, you just scale it. It's typically written as a lambda, but
Okay.
you're right, it's just a.
Yeah, it's a one-dimensional vector in a particular direction defined by the matrix. And just that scales. It just.
Yeah. and for,
Okay.
and for example, in principal component analysis, that's how you find them. It's you calculate
Yeah.
you calculate the eigenvalues.
Mhm.
And, but what you're doing is you're changing the coordinates.
Yeah.
So you have, if you have data, you find the axis where most of the data is, in a sense,
Yeah.
what's the
Kind of collinear kind of bundles around.
bundle?
Yeah.
That's my English no good, you know. And then the next one is perpendicular to that.
Okay.
And then in 3 dimensions perpendicular, and then in n space and so forth. And then that's how you kind of sift out the correlations and you get to those primary components that drive,
Yeah. Okay.
either.
Not sure I get it yet, but that gets me at least closer than I've gotten in many years. Especially for somebody who doesn't do this stuff like ever.
Well, there's a lot of beautiful things about this too. So if you have a matrix that's n by n, typically you'll have n different vectors that have that property. So it's not just a single vector with respect to the matrix. There might be n different ones that have that property. And sometimes it can be 0.
Okay,
Sometimes there's certain vectors that if you apply the matrix to it, it'll just zero it out. So
okay,
it's, the vectors, the set of vectors that do that is the quote null space.
okay.
The matrix kills those.
Okay.
There's only, I think.
That gets me a little closer. Maybe in another decade I'll have it mastered.
It's powerful because you can,
Yeah.
it lets, like engineering, or math, or whatever, it lets you kind of treat a system, this complicated system of equations with, n by n matrix, kind of just as individual.
Yeah, it gives you the
Just as
principal
a
components.
scalar. Just that,
Yeah.
right.
Thank you.
Would you like to give a lightning talk on the topic?
Yeah.
Yeah.
Yeah, we'll have some in September.
Actually, maybe I should.
Oh, no, I don't want to talk about it in September. If I can do a lightning talk, it'd be our graph algorithms proposal,
Oh,
Mm.
okay.
advancing the.
That'd be cool too.
Maybe I can go back and dust off my linear algebra. I mean, I use them, but I don't have the elegant explanation.
Yeah, I'm the other.
There was a time when I could explain it.
I don't do it much, but it's like, I keep brushing up against it from time to time, and it's like, if I knew that, I could probably solve this much easier and better, right?
This is Bob Goddard. This is something I use a lot, is these correlated, I use
yes, you
a
do.
correlation matrix in order to generate correlated random numbers. And the Cholesky factorization that you mentioned works if the correlation matrix is non-singular. And it fails disastrously if if the correlation matrix, if, for example, you have perfect correlation between A and B, so that you have maybe, if it's two-dimensional, you've got two eigenvalues, and one is much larger than the other. So almost all of the correlation is explained by some linear relationship between the two variables. If that happens, and it happens a lot in my applications,
Interesting.
Cholesky factorization fails disastrously. And so in that case, you can do the same thing and generate correlated random numbers using eigenvalue eigenvector decomposition instead of Cholesky decomposition, because the it's a little bit more complicated numerically and takes longer. But if you have it particularly works if the matrix is let's see now, poorly sorry. So the ratio of the values of the different eigenvectors is large. The ratio of the largest eigenvalue to the smallest eigenvalue is large. Then the matrix is nearly singular, and you can't do a Cholesky decomposition. You have to revert to eigenvalue eigenvector decomposition, which is more stable. So you can do the same thing in several different ways, but it doesn't come out. The nice thing about Cholesky is that your answer comes out triangular. So you only have a little over half as many numbers to deal with when you're done. So it's more compact and it's a lot faster. But I just want to put in a bit of caution that if what you want to do is generate correlated random numbers given a correlation matrix, Cholesky works only in the nice cases,
Which is what you typically find in finance.
So depending on what you're trying to do and what your precision accuracy requirements are, you can just add a little bit along the diagonal and all of your.
Oh yes, that's true. But it's where I work in physics. It's
Yeah,
often you have very, very large correlation matrices. If you have, you want to know the correlation between two hydrophones in an array that has 1,000 hydrophones in it, then the chances are rather remote that that 1,000 by 1,000 matrix is going to be well behaved. So,
But in physics, I mean, if you think for physics in the real world has a lot of diffusion, so adding something to
adding 10 to the -6 on the diagonal is
Yeah.
probably okay
Yeah, the real world's that way.
eventually.
yes, that is one way to do it, but it's kind of arbitrary, and and you get something close to the right answer, but it's not really the right answer. And you could, by investing a little bit more in the computational effort, you can get to the same kind of an answer and generate correlated random numbers with the correct correlation matrix if you do it via eigenvalue eigenvector decomposition instead of the Cholesky decomposition. So I just want to investigate that little, inject that little bit of realism that if your systems get large, as they do in a lot of physics problems, that you have to get it more sophisticated as to how you generate correlated random numbers. That's all.
Okay, yeah, thanks. Also, I should have added too, when I'm talking about this there, you might have noticed there's like in StudBLAS, there's a symmetric option, and you have that in Eigen, but I just keep the example simple, even though we're dealing with a symmetric matrix. I just used a regular. But
yeah, the correlation matrices are always symmetric, or
right, yeah,
but they're not always positive definite. Sometimes they're positive semi-definite, which means that some of the eigenvalues are going to be 0 or close to 0 from a numerical point of view.
right. But those options exist both in StudBLAS and in Eigen if you want to use them. But
Well, one little bit of trivia, or kind of going back to this example, the eigenvalue, eigenvector. So this is kind of going in one direction, right? So you have the vector B, A times B equals this. Suppose you have this and you want to go back in the other direction, right? So you divide by C. But if you have that case where, we talked about A kind of kills B at C is 0, you can't go back the other direction. You can't find the V such that A times that B will give you a. That's what's happening in this case.
Okay.
The classic is it blows up, or when we're thinking about, you have a singular matrix, it'll.
And then adding the little delta just pulls it off of that value.
Yeah, so
Pulls it off of that.
yeah, so you always have, so it's an A plus, some small
Yeah.
identity, right? So you always have, if A times V is 0, or 0, there's still this epsilon times V. It changes this a little bit, but if this is really small, then that's a G-min.
So folks, we got about 10 minutes left. I'm gonna go, we're done with questions. I'm gonna go have them stop the video. And we'll start kind of filtering out so our hosts can go home for the evening. Just a reminder, next month we will be a half hour earlier. So our hosts can go home a little earlier.